Greetings, everyone. This is Mr. Mull. Today I'm just going to do a really short podcast for you, just talking about some ideas, some terms that we've used or we've heard or that we're going to need to know as we enter into the last couple of days here. So first off, I want to talk about the word net force, and then we'll talk about inertia and Newton's third law again. So what do I mean by net force? So when I'm talking about a business, okay, so I'm in the business of selling lemonade, and I go and I make $100 selling lemonade. The problem is I had to go to the store beforehand, and as I'm counting my 100, I realized, well, shoot, I spent $20 on all those supplies. So my take home at the end of the day wasn't the 100, it was actually the $80. So what was my net profit? $80. When we're talking about forces, the net force, we're talking about what's left over, the leftover amount of unbalanced force that is causing an object to accelerate. So when I have some object, and I'm just going to make up some object here, and I'm pushing some crate along, let's say I have a crate on the ground, and we're giving this thing a push. So I give this thing a big push, and I push with everything I've got, 100 newtons. But I'm sliding across the surface, and there's friction. Turns out there's, let's just say, 50 newtons of friction. Vertically, let's say it's 100 newtons of normal force and 100 newtons of gravity of the Earth. So when I'm looking at this to try to find the net force, I don't have to worry about the vertical forces at all because they're already balanced. But these forces that aren't balanced, we would actually, and we could make a net force equation. The net force, or the overall, mathematically, I'm going to keep that 100 positive, and we're going to subtract that 50. So my net force is 50 newtons. So the net force is the leftover unbalanced force that is actually causing the object to accelerate. So if I'm watching this object, what's actually causing it to accelerate? It's the 50 newtons that's kind of uncontested. So this is a net force. This will help you on the horse cart problem. Next thing I want to talk about is this idea of inertia. I want you to think back to the bowling ball lab. You were hitting that bowling ball with a mallet, and clearly the bowling ball was harder to get going than you thought it might be, and then once it got going, as it's going down at the end of the hallway, you're going to try to start to change its state of motion, and you realize it's harder to get it to stop moving than you may have thought it would. So this phenomenon of inertia is a property of an object, and it refers to the object's resistance to change its state of constant velocity motion. Okay, so when I say constant velocity motion, I'm saying it's moving at a constant speed, okay, some value here, or so it's moving along and I'm trying to change the state of motion, or it's at rest. Okay, either one of those are constant velocity motion. So from Newton's first law, if it's at rest, it wants to stay at rest. If it's in motion, it wants to stay in motion. And inertia is this property of an object to want to keep doing whatever it was doing. It is not an interaction between objects, therefore it's not a force. The other thing about inertia is the more mass an object has, just like with the bowling ball, if you were beating around basketballs, that whole bowling ball lab would be very different. Because the more mass that your object has, the more noticeable that property of inertia is. So we can say that mass is actually a way to quantify how much inertia an object has. Okay, how much inertia an object has. Last but not least, I want to look at a Newton's third law. Just kind of restate it again. Trying to overcome this idea that forces really do come in pairs. They really do act on the other object, and they always are equal and opposite. So when we're looking at Newton's third law, a way that you can think about it is that you cannot touch without being touched. You cannot pull without being pulled. And then kind of another piece to it is that you can only touch as hard as you are touched. You can only pull as hard as you are pulled. So when we have this tug of war here, if all of a sudden this person can pull harder than this person can handle, so let's say for example right now they're at rest and there's some friction force on the ground with the shoes, and right now it's balancing out. Well, as soon as this person pulls any harder, and this goes up, and this goes up, okay, because those are going to be equal. If the force of friction on his shoes cannot balance out, the new force of the pull, well, then this guy starts to lose, and then he goes the other way. They always feel the same force, but the reason why this guy starts moving in the other direction is because there's nothing there to balance it out. Okay, there's nothing there to balance it out. And so you're going to kind of explore this idea today in that horse cart problem. Well, I hope this was helpful, and I will see you on Tuesday.